Okie doke. So we've looked at for resource extraction and use of non-renewable resources. We've looked at three sort of special cases in isolation. Now we're going to look at what if there's a resource that initially is super abundant, we're just scratching the surface, nothing happens to depth. Then we have a constant flow, and then it starts running out. Can we combine all that in one model? Sorry. It turns out that we can. And that's what we're going to look at now. And that's actually my paper from 2016 in the Journal of Economic Dynamics and Control. But here we're gonna, in this video, or it'll probably take 2 or 3 videos, we're going to go through a simplified version. But I do want you to look at the paper as well. Okay, it's slightly different the way it's set up in the paper, just so you're warned. Okay, consider the picture below, and with its help, try to identify as many such factors as you can. What factors? Oh, sorry, this is sort of a cut and paste. I think I've changed things. It's factors affecting the cost of resource extraction. And should they make extraction costs rise or fall over time? So you might want to pause the video here and have a think about that. Okay, but now I'm going to tell you. So we got somebody working with the help of some capital, the shovel, to extract resources. Clearly, if the wage were to go up, or the price of capital were to go up, that would push extraction costs up, right? On the other hand, if the worker got more productive, or if they got more productive capital, so the worker capital combination got more productive, that would push the price down. And finally, I think, if the depth of the stock increased, as you dig more and more, you have to go deeper, that is presumably going to push the price up, right? You have to work harder to get the resource to the surface. And that will happen faster if we think of the left-hand stock, process will be faster, right? So prices will tend to rise faster with the left-hand stock than with the right-hand stock. Okay, so this is the kind of thing we want to capture in our model here. So let's see what the model, well, here is the model. What's going on here? So we've got final good production is AY, LY, so this is effective labor inputs, times to the 1 minus alpha times the resource flow to the alpha. Okay, so we've dropped capital. Since we're always looking at balanced growth paths anyway, capital doesn't make much difference. Sorry, just going to take some tea. Okay, so that's final goods. What else is going on here? Yeah, so we're going back, by contrast to a couple of videos ago, we're doing the more intuitive thing where labor is the input to the mine, not final goods. Okay, and so now productivity increases affect labor in the mine and labor in the final goods sector, and we actually differentiate between those, so they could grow at different rates. Okay, theta AY, theta AX, LY, LX. Okie doke. And then what's the flow of extraction? It's LX times AX, so that's effective labor inputs, divided by AD, where AD is the difficulty of getting the resource onto the truck. Okay. And AD, we say, is the e to the power of d, where d is the depth. Okay, so that's the model. It's, as I said, it's done slightly differently in the paper. It's effectively the same, but it's just a bit of a tweak on this. Okay, so that's the setup. What happens? Or we need to do a bit of math. So what's going on over here? So we've got d dot is x over phi. Phi is, here it's sort of 2d, so that's the width. Effectively it's the surface area of this tube of resource. So d dot, the rate of increase of the depth, is the rate of extraction divided by the surface area. That's just like physics. Okay. And then AD dot here, if we look here, what's the rate of change of AD dot of AD? That's dAd by dt. Sorry, not the rate of change, just the change. It's dAd by dt, dd by dt, right? So how much does AD change with time? It's how much AD changes with d, and then how much d changes with time. dAd by dd is just AD, right? That's differential of an exponential is the exponential. And this is d dot. So AD dot is AD d dot. In other words, the rate of increase of AD is d dot, which is x over phi. Okay. Right. So what happens? And I'm going to take a quick pause.